Next up on the docket is esters. But like I've promised you, before we get too far, we got to remind ourselves of all the derivatives in the top corner of our board. Yep, you got it, board. So the most reactive carboxylic acid derivative, hopefully you're starting to know this list by now, is an acid chloride. Then comes an anhydride. And then today's beauty, an ester. And then an amide, and then a nitrile. And remember, carboxylic acids are over to the side. Why are they over to the side? Because carboxylic acids can be used to make any of these derivatives, except that one. And carboxylic acids are the side step when you want to convert a less reactive derivative to a more reactive derivative. Okay, so getting started with naming esters. Esters all have a singly bonded oxygen on one side. We're going to call this on the single bonded oxygen leg because that's what I do. When you name an ester, you have to name the thing that's out here on the leg first. And then you name the rest of the molecule as if it were a carboxylic acid. So this is 2 carbons. So a 2-carbon carboxylic acid is acetic acid or ethanoic acid. But because it's an ester, you drop the ic acid and name it an ate. So it's an acetate or an ethanoate. But the first name has to be the name of this leg out here. 2 carbons is an ethanoate. This is a phenyl out here. It's a benzene directly connected to the leg of my oxygen. Phenylpropanoate, because there are 3 carbons in my what used to be a carboxylic acid. Since these already have names given, we're not going to talk through any more of them, but there they are for your viewing pleasure. Lactones, on the other hand, have a little bit more information for us to talk about. Lactones are cyclic esters. So all of these guys up top are cyclic esters. They are lactones. The way to name a lactone is how many carbons are in the molecule in total? For a common name, sorry, I should specify. For common naming, how many carbons are in the molecule in total? 1, 2, 3, 4. 4 carbons. So the common name for a 4-carbon carboxylic acid is butyric acid. So butyric acid is the root acid name that this thing comes from. But then you have to recognize that it's wrapped around as a cyclic ester molecule. So you don't name it an 8, like I just said, we named esters 8. When you recognize it's a cyclic ester, you name it a lactone. So you keep the butyro part, butyric acid, you keep the butyr part, and it's named olactone now. Butyrolactone. I know, isn't it fabulous? Where the heck does this front letter come from? Well, the carbon next door to the carbonyl carbon is the alpha. We said that a couple days ago. The carbon next door to that, oh man, it's beta. The carbon next door to that is gamma. So the gamma carbon is the carbon that the singly bonded oxygen leg is connected to. The gamma carbon is what closes up your ring. So that's why it's gamma butyrolactone. This is a valorolactone because there are 5 carbons in total, and valeric acid is the root of a common name. Alpha, beta, oh boy, gamma, delta. This one's delta because that's where the oxygen closes up that ring. Thankfully, Dr. Bruce already wrote the alphas and betas and gammas on this one. It's a caprolactone because there are 6 carbons in total in that ring. It's in that molecule, sorry. It's not just the carbons in the ring. It's 6 carbons total in that ring. Dang it. It's 6 carbons total in that molecule. Molecule. Just like class. 6 carbons in total in that molecule, regardless of how many are in the ring. But you name it a delta caprolactone because that's the bond that's closing up your ring. This guy, gamma caprolactone, 6 carbons in total, and it's the gamma, the 3rd carbon away from the COO that's closing up the ring. Blah, isn't that awful? common naming of lactones is wacky. So IUPAC came in and said, let's make a little more sense of this thing. So the first bit is recognizing that it's a 5-carbon ring or a 5-membered ring. So it's a cyclopent because it's a 5-membered ring. It's a pentanone because they're calling this group up here a ketone. It's incorrect to really refer to it as a ketone functional group, but nomenclature-wise, that's how these lactones are named, because there's always this other piece that says there's an oxygen. Yep, oxygen in my ring also. So the 2-oxa refers to, this is carbon 1. This here is carbon 1. And so the oxygen is on the 2 position within that cyclo ring. So 2-oxacyclopentanone, while you may not love that name, I bet you like it a little more than the red one below it. There's 6 carbons and 6 members in this ring in total. So it's a cyclohex. It's a cyclohexanone. That's naming this ketone looking thing. But it's a 2-oxa to tell me it's really an ester, a lactone cyclic thing. Hopefully you can walk through those couple of names. Let's talk about this guy down here together. So naming that ester on the left. We are not doing common naming of this guy. We are only doing IUPAC. We name the side over here as a carboxylic acid. So that's 5 carbons in total. So that's a pentanoic acid. But recognizing it's an ester, it's going to become a pentanoate. But is that simply pentanoic acid? No. There's a bromine hanging off of this pentanoic acid, or this pentanoate. It's a 1, 2, 3 bromo pentanoic acid if you had it as the acid. So it's 3 bromo pentanoate. And so those are all smushed together as one word. That is all smushed together. On the other side of the ester, the single leg thing, you need to name that thing separately. So we're naming this thing separately. And we're saying this thing has 4 carbons, so it's a butyl or a butane. It's a 2-methylbutane. But this whole thing was connected to my ester, so it's not an ane, it's an ol. So this name becomes 2-methyl-butyl with a space, 2-methyl-butyl space, 3-bromopentanoate. The pink part before the space tells me that's the leg of your ester. That's the thing bonded to your singly bonded oxygen. And then, a lactone. If we name this lactone, we will do common and IUPAC. Common for this guy, 1, 2, 3, 4, 5 carbons in total. So it's a valerolactone. And that bond here is what we need to refer to, alpha, beta, gamma valerolactone. IUPAC for this guy. It's a 5-membered ring. So it's cyclopent, anone, to account for this COO carbonyl. It's a 2-oxa because all lactones are going to be 2-oxa. And then it's a 3-methyl. So this actually does not have any spaces. It's all jammed together, 3-methyl, 2-oxa, cyclopentanone with dashes in between these guys. Here's to hoping we got it right. 2-methyl-butyl, 3-bromopentanoate, ding ding. Gamma valerolactone, check check. 3-methyl, 2-oxacyclopentanone. Whoop whoop. All right. So rather than continuing to talk about nomenclature for the next 14 minutes, we're going to talk about what reactions esters do. Esters are different from the other derivatives we've talked about in that they can change from one ester to another. That's called transesterification. Esters can be converted to amides, just like we talked about so much yesterday. More reactive derivatives can be turned into less reactive derivatives, so esters can be converted into amides. And like all carboxylic acid derivatives, all carboxylic acid derivatives can be hydrolyzed to become carboxylic acids. Esters are important in these types of compounds, and we'll actually peek a little bit into these types of compounds in a minute. All right, mechanism number 1, transesterification, turning one ester into another ester. All right, starting with this ester, this alcohol, and an acid catalyst, let's do a transesterification, changing one ester for another ester. In all those reactions from the most reactive derivatives, acid chlorides and anhydrides, the first thing we did was attack the carbonyl carbon, but not here. Esters are a little bit different from those because they're starting to cross the threshold of this carbon is not partially positive enough for many nucleophiles to just attack straight out of the gate. This carbon needs to become more partially positive in order to be attacked. And so what we do is we protonate that carbonyl oxygen. Because protonating that carbonyl oxygen causes that carbon to have more partial positive character, making it more susceptible to attack the carbonyl carbon, like that. Because this reaction is acid catalyzed and it's an ester, it starts to be too stubborn. Esters are too stubborn to react without protonating them first, without protonating the carbonyl oxygen first. So we get here. This is starting to look like a tetrahedral intermediate, but it's not quite there yet. Not quite to the official neutral one that I'm aiming at. Some base in solution comes to clean up that extra proton to get me here. This is a tetrahedral intermediate. This tetrahedral intermediate is neutral. All the ones we saw previously with acid chlorides and anhydrides were negatively charged. Well, you can't make a negatively charged intermediate when you're an acid catalyzed mechanism. So this guy is as good as it gets as far as tetrahedral intermediate is concerned. One more thing. Yesterday, when we had that negative tetrahedral intermediate, we could fold down and kick out at that point. Not here. If we tried to fold down and kick something out at this point, we would be losing an O-. Do you think an O- is going to be kicked out when this reaction is acid catalyzed? I think not. So what we got to do here is make a better leaving group so that then we can let it leave. Who's going to be my better leaving group? This is a transesterification reaction. So because it's a transesterification reaction, we want the original ester leg to go away. We want the original ester leg to go away. So it's that thing that we protonate to make it a better leaving group so that then we can let it go, let it go, let it go. We can't hold it back anymore. There it is. Fold it down, kick it out. This is where we're ready to fold down and kick out. When we have an acid catalyzed mechanism, we fold it down and kick it out when we're losing a positively charged intermediate. When we're losing a positively charged thing. Right now I can't think of the word. Sorry. Whoops. So I folded down and kicked it out, but I kept my H in place. This is ready to be cleaned up, and then it's finished. Speaking of Easter, whoops, you can't see that, and I can't scoot it any further. Trans-esterification, turning one ester into a different ester. We turned our methyl ester into an ethyl ester. Whoop, whoop. Moving along to the next example, that also says it's a trans-esterification. And that molecule looks darn similar to the one we just saw. What's so different about it? How does this one work differently? You'll have to tell me. Moving right along, we said esters can be turned into other esters, but esters can also be turned into amides. Here's this one. First thing to note while I'm still drawing this example, is it acid catalyzed? No, this reaction is ran in base because this is an ester plus an amine, and amines are bases. So there is no acid to make this ester more reactive, to protonate the carbonyl oxygen, make it more reactive. So therefore, attack right out of the gate. Oops, that's not an H. Looks like a little frog. If that's not legible, I apologize. This is just a 3-carbon leg with a scribble. So this time, because it's not acid catalyzed, it behaves a lot more like the mechanisms we saw with acid chlorides and anhydrides. Attack the carbonyl carbon. Some base comes to clean up. Who is the base in this reaction? Hopefully you watched the addendum video and this is clear. Some base comes to clean up. Then you have this anionic tetrahedral intermediate, and you're ready to fold down and kick out your weakest base, your best leaving group. Now, is that thing I kicked out a very weak base at all? No, it's actually a strong base, according to where we've drawn our line of strong bases and weak bases. It's a strong base, but when I fold down and kick out, my options are kicking out an O-, an N-, or a C-. Given that selection, O- is the weakest of those choices, so it's the best option. You can convert an ester into an amide because an ester is more reactive than an amide. So you're converting a more reactive derivative into a less reactive derivative, just like all the others. This mechanism, things of note, this mechanism cannot be acid catalyzed. Why not? Because amines are bases, and if you add an acid catalyst to this mixture, you're going to destroy your nucleophile. If you added acid, you would get this guy with 2 H's and a plus charge. When you take his lone pair away, he cannot be a nucleophile anymore. So this mechanism, turning an ester into an amide, cannot be acid catalyzed. In addition, it is typically ran with 2 equivalents of this amine. Why? Hopefully you know the answer. I think I'm going to make you answer it. Moving on. We said esters can be turned into other esters. We also said esters can be turned into amides. And esters can be hydrolyzed. Just like all carboxylic acid derivatives, they can be hydrolyzed. And when they're hydrolyzed, they're turned into carboxylic acids. Let's do a mechanism. So we're going to call this acid catalyzed hydrolysis because there's acid in solution. Just like the first mechanism of today, when you have acid in solution, the first step is protonate the carbonyl oxygen so that carbon, the carbonyl carbon, becomes more electrophilic. It becomes more susceptible to attack the carbonyl carbon, like that. Hydrolysis, cutting with water. Water is the attacker. So I get this guy. It's a tetrahedral intermediate that looks so similar to the tetrahedral intermediate from my transesterification. But what do I got to do? Clean up a hydrogen, clean up a proton, so that I can get to my neutral tetrahedral intermediate. Ester reactions go through neutral tetrahedral intermediates when they are acid catalyzed. Here's my neutral tetrahedral intermediate. So I'm ready to fold down, kick out? No, I'm acid catalyzed. I need to make a better leaving group before I fold down and kick out. Who's my leaving group? Well, I'm hydrolyzing an ester, and hydrolysis really means cutting that bond, breaking the bond between the carbonyl and the heteroatom next door. Hydrolysis of an acid chloride, it's between the carbonyl and the Cl. Hydrolysis of an anhydride, it's hydrolysis between the carbonyl and the singly bonded oxygen. Hydrolysis of an ester is between the carbonyl and the singly bonded oxygen. So I'm going to turn that singly bonded oxygen into a better leaving group so that it can go away. Like that. Fold it down, kick it out. Ta-da! Almost finished. Clean up that final proton, and then really, you're finished. There is my final product. My ester has been hydrolyzed to a carboxylic acid. We're going to talk about this one some more, but before we talk about this one some more, let's draw the mechanism for hydrolysis of an ester in base. Top guy, acid, bottom one, base. Not acid catalyzed. Do not protonate the carbonyl oxygen first. Do not pass go. Do not collect $200. Base catalyzed. Attack the carbonyl carbon. Straight out of the gate. Attack the carbonyl carbon. Like so. There's my tetrahedral intermediate that is anionic. More similar to what we saw when we made an amide just a minute ago, or what we saw previously with acid chlorides and anhydrides. When you have an anionic nucleophile, it means you're going to be in basic solution / not in acidic solution. So you're ready at this point to fold down, kick out. Fold down, kick out. Why am I kicking out there? Because I'm hydrolyzing an ester, and I'm hydrolyzing it. No, I'm hydrolyzing an ester, period. Finished. End of sentence. Sorry. Uh-oh. There's a tricky thing that happens next. But you know your acid-base chemistry, so hopefully it's not tricky to you. This is the conjugate base of what functional group? This is a carboxylic acid. These things cannot coexist in solution. So you will get a proton transfer between the conjugate base of the alcohol and the carboxylic acid because those guys cannot coexist. So you end up with a carboxylate. carboxylate, and an alcohol. Got it? Cool. Base hydrolysis of an ester is officially called a saponification. Hydrolysis in base, saponification. Hydrolysis in base, saponification. Hydrolysis in acid, no fancy name, just hydrolysis in acid. So if we compare these two things and we tidy up this hydrolysis in acid reaction that I drew for you earlier, I did something that I shouldn't have, or I neglected to do something that I should have. This reaction is entirely an equilibrium process. The whole shebang is completely reversible. Every single step in here, completely reversible. What does that mean? Why do I care? Well, how do I favor the formation of products in a completely reversible reaction? We called this reaction hydrolysis, and we added a bunch of water in order to do our hydrolysis. So the hydrolysis of an ester in acid, completely reversible. Le Chatelier says if you add tons of water to this reaction mixture, you're going to favor formation of the products because water is a reactant. So you can get a decent yield, a decent amount of product when you do this reaction in acid. But you generally get a higher yield when you do this reaction in base, because the base reactions are reversible for the first couple of steps. This step of kicking out that functional group, kicking out that O-, that step could be reversed. This could go backwards. But this final step is irreversible. This final step where you exchange protons between the two is irreversible. And when you make a carboxylate, that carboxylate is not partially positive enough for this to ever attack that carboxylate. Carboxylates are very unreactive. There are a couple of things we will see that react with them, but in general, carboxylates are very unreactive. That carbonyl carbon is not susceptible to attack. It's a little bit partially positive, but it's even below nitriles on the list of reactivity. Carboxylates are not very reactive at all. So if you compare acids and bases, if you compare hydrolysis in acid and base, hydrolysis in acid is a totally equilibrium process, and you can favor one side or the other by manipulation of your conditions. Hydrolysis in base is said to be an irreversible process because this last proton transfer step is an irreversible step. Equilibrium favors this product so heavily that we say it could never go backwards to this protonation state. So there are advantages to using acid over base practically when you are in the lab trying to do this experiment, like the Fischer esterification lab that we missed previously. So we drew the mechanism for hydrolysis of an ester in acid, but we did not talk about this. This is related to what we said a couple days ago with the experimental evidence to prove that the mechanism is as we say it is. If you isotopically labeled this carbon up here and went through our entire process, as it turns out, in the end of this reaction, the O18, the isotopic label on oxygen, is found in both oxygens of the carboxylic acid as well as in water. There is absolutely none in the alcohol. So this oxygen has to have come from, or has to have been, this oxygen in the beginning, because otherwise it would end up with an O18 label sometimes. The isotopic label is found here and in water. So that tells you that it is a reversible system. Things are going back and forth equilibrium-wise unless you manipulate the conditions to favor only products. Yep. We drew this mechanism, tried to saponify that guy. Saponification means hydrolysis in base. We've said hydrolysis of all of the carboxylic acid derivatives results in carboxylic acids. So hopefully you can predict the products for all three of these reactions. That top one, carboxylic acid, product. The middle one, carboxylic acid, product. The bottom one, carboxylate, product. For the bottom two that are both esters, the middle one especially, there's another carbon piece that you will lose, so make sure you predict that as part of your products. And then for the bottom one, make sure your protonation state is appropriate for being hydrolyzed in base. You should do these on your own, and maybe I can start the next video with the answers to these, but you should do these on your own first. All right, we're going to spend a quick last minute talking about where esters are found in other systems. For one, esters are found in phospholipids. There's an ester, phosphatidylcholine, phosphatidylethanolamine. These are important constituents of cell membranes. Phosphatidylcholine is the most common lipid found in our membrane bilayers. It's a large percentage of our membrane bilayers. One thing that esters do, and these lipids do, is they regulate signaling pathways within our bodies. So there are some enzymes that will cleave this ester bond specifically, making that lipid no longer part of the bilayer. It will send it into the cell to signal some other event to happen. In addition, there are esters that cleave this ester bond specifically. Same cascade of events as before, but they signal different processes. One more thing while we're at it, there are other enzymes that cleave off this phosphate head group. You got it. It signals certain pathways as you cleave that group. Esters are also found in triglycerides. A quick little story for you. Instead of switching back to the camera, I guess I'll just tell you without drawing things. Nope, I gotta draw things. Esters are also found in triglycerides. What are triglycerides? Triglycerides, I bet you've heard of them before, but they're triacyl glycerols. They are fats. Triglycerides are fats that are found in our bodies. These fats can have lots of configurations along these fatty acid tails. These fats, this triglyceride, is a fat, and it has 3 esters as part of this fat. Have any of you ever made soap? Yeah, really, soap. The way soap is made is you saponify fats. Those fats can be found in oils like olive oil, avocado oil, coconut oil. Those fats can be found in lard, things like butter, things like human fat. What? Yeah, give me a second. When you saponify this thing, you end up making a glycerol and 3 fatty acids. Why am I drawing them as the O- version? I think I drew too many carbons. Oh, I think it's right. Why am I drawing it as the O- version? Because it's hydrolysis in base. So the composition of a triglyceride, whether the triglyceride is a fat that's solid at room temperature, a fat that's oil at room temperature, the composition of the triglyceride determines that. If you have all saturated chains, you will have a saturated fatty acid. All saturated chains are likely to be solid at room temperature. These 2 guys have unsaturated chains. potentially oil, potentially liquid at room temperature. So many oils have unsaturated chains. Saturated chains are things like butter and lard, animal fats, pork fat, bacon fat. Delicious. These that have unsaturated chains likely to be oils at room temperature. This guy has a bunch of trans double bonds. This is what the marketing industry calls a trans fat. If there are 3 chains that all have trans double bonds, trans fat. This is officially called an omega-3 fatty acid because the end of the chain is the omega. Count back 3 carbons and you've got a double bond. This is omega-3 fatty acid. It's actually also an omega-6 and an omega-9. But if you have a bunch of cis unsaturations, that's supposedly a good thing. Fish oils and things like that come from cis unsaturated fats. So saturated, trans fat, and polyunsaturated fish oil stuff. Depending on the composition of your chains, you'll get different types of triglycerides. Nevertheless, when you hydrolyze, when you saponify these triglycerides, you get glycerol and 3 free-floating fatty acids. These free-floating fatty acids are soap molecules because there's this non-polar bit that can associate with the oil on your skin, and this polar bit that makes a micelle around your oil and washes your oil down the drain. Where is my favorite example of this in action? Obviously, it's in Fight Club. If you've never noticed, on the cover of Fight Club, he's holding a bar of soap. And there's a clip where he talks about the process of making soap. Why the heck do they make soap in Fight Club? Well, the reason they do is they're really wanting the glycerol component. And if you watch it closely, his science is a little bit whack, but he talks about taking that glycerol, adding a little bit of nitro and sawdust, blah, 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 and you get dynamite. Do you remember that nitro compounds are potentially explosive? Yep. So if you haven't watched the whole plot of Fight Club, even though we're not supposed to talk about it, we're going to. They start out by sealing human fat from a liposuction clinic, and then they hydrolyze that fat. They saponify that fat using lye, which is sodium hydroxide. They skim off the glycerol layer and are left with the fatty acid layer. That's the actual soap, the fatty acid layer. But they skim off the glycerol, add some other things to it, and that's why the building explodes in the end. If I ruined it for you, I'm sorry. Next time, amides.